Hi students, the main question we will answer in this record is about state space modeling with input derivative. So again, state space modeling with input derivatives. So up to now, we know how to represent a model, how to represent a physical system, how to represent your plant in state space representation if it is in that form. If it is in that form. That's what we saw in previous records. But now what happens if the system contains derivatives of the input u? Contains derivative to the order n, if you wish, of the input u. So if your system or your physical system, your plant, is in this form, that's the ordinary differential equation or the equation of motion. Okay, that's it. If it is like this, how to represent it in state space? Okay, that's the main question we will answer. How to represent a state space with input derivatives. Like, take this example. In here you have the equation of motion or the ordinary differential equation, and with the derivative of the input u. So if your system has an input u and an output y, the displacement, the force applied, in which the force is proportional to the u prime. Okay, so if this is your equation of motion, how to get the state space representation, basically A, B, C, and D. Right here, taking into consideration this is a single input, single output system. This representation is for a single input, single output system. Okay, so maybe we can give another example. Maybe not like this, but like this. If you have a system like this, and its equation of motion represented by the following. So with input derivative. So again, u and y. So how to get A, B, C, and if there is D? Okay, that's the main question we will answer here. Well, up to now in the previous sessions, we saw that the steps, you have 4 steps. If your equation of motion, you see it's not input derivative. 4 step, what's the order of the system? Order defines the number of state variables, defines the state variables, and identifies the input in your state space model. Third step, express the derivative and in terms of the states and the controls. So you can write it this way. So it's the state equation and the output equation. Good. So those are the 4 steps that we saw previously. So now, if we want to apply them, let's take this example and we want to apply them. Second order to states. I cannot write it if it is this way in terms of u, because you have here u prime. You should write it in terms of u so you can have the state space representation. Okay, so actually what we take is the following. As state variable x1 and x2. So in a way, we want to eliminate this u prime. And therefore, if you look at it now, my x2 prime looks like this. Now the state space model can be expressed as the following, where this is A and this is B. So you see it's written now in terms of U. So you can find A and B. Okay, if it was U prime, you cannot. So that's why we impose x2 equal to this. Actually, the one we are getting it always U prime, but in addition we added B over mu. Why you added this B over mu? because we want to get rid of b over m u prime plus b over m u prime, so we added minus b over m u. So the derivative of it will cancel. You see here they are cancelled. Okay, so the remaining parameter is u. Good, so that's the way we go for. Okay, now let's generalize it. So assuming this is my system in which the equation of motion or the ordinary differential equation is related to the derivative of the input u, maybe n times derivative, its derivative, the nm derivative, right? So then it is in this form, so you write it in this form. You write your equation of motion or the ordinary differential equation in this form. So here you have 1, okay, so I write it in blue. So here you have 1, here a1, an minus 1, an b0, etc. Also you could write it in a transfer function form. From ordinary differential equation you can easily convert it to a transfer function. Keep in mind this is a single input, single output system. Okay, so then the general form, you can directly express your state space representation in this form, in which your matrix A is this one, matrix B is actually 0, all 0 except the last one is 1, and your matrix C is this is the first column, second column, etc. plus B0U. Okay, this is the B0. This is the A1 up to AN, and those are B1 up to Bn. B1 up to Bn. Alright, so this is your matrix C, and this is your matrix D. Keep in mind that it's a single input, single output system. It's a CISO system, but I'm representing it as the mass spring damper system we saw in a while here. So instead of going over it and think what states I want to impose, you can do it this way and figure out. But a general way, if you have a system like this, so you can directly write it in this state space representation. By the way, this representation we call it controllable canonical form. Controllable canonical form. Okay, see it, it's controllable canonical form. Keep in mind that the state space representation are not unique. We have the non-uniqueness of the state space representation, so your colleague could have a different state space representation. So this is one of the form of a state space representation for the system, and this form we call it controllable canonical form, just for your own interest if you want to know the name of. But basically that's it. Let's see an example. So now I'm having this example and I'm asking you, you see the it is in the second member of equation is related to the derivative of the input, and this is your equation of motion. We ask you to find the state space representation, so to find A, B, C, and basically D. Okay, so now we are not imposing state variables and going from step 1 to step 4. No, directly I went to my canonical form, state space canonical form, controllable canonical form, in which just my matrix A, B, C, and D. So you see B is the all 0, 1. Okay, and this is a matrix A, this is a matrix B. So first step is to write it in that form. Remember, here you should write it in a way that you have here 1. You see, you have here 1. And that's how you write it. So now by identification, you can get A1, it is equal to B over M, A2 equal to K over M, etc. So you have the variables you need. So then you go and plug them here, A1 and A2 minus k over m, and here is 1 0. Okay, so then you get your directly get your matrices A, B, C, and D is equal to 0, because B0 is equal to 0. Okay, your matrix D is B0. So you see, so then it is easy if you wish to go in this general form.